Yes, so we can now move to the invited presentations. The first one is by Marvin Reich at GFZ. It is about advanced and challenges in hydrogravimetry in applied field studies.
Yes, hello. Can you see my screen?
Yes.
Okay. So thank you very much for inviting me to this very interesting workshop we've seen with very interesting talks. And I will give you a little bit of an idea how advances and challenges were faced and met and resolved in the context of hydrogravimetry. So it's a little bit out of this geothermal volcano activity topic, but I hope you can take interesting ideas out of this. So I will talk about 4 different subjects, basically. More general overview, what has been done and what challenges still exists with respect to resolving hydrological signals with the method of gravimetry. I will talk about an acreage field campaign we carried out, about hydrogravimetry a little bit in general, and about another big topic of data processing. And for each of those, I will address advances made and challenges that still exist with respect to each of the topics. So starting with resolving hydrological signals. So when the hydrologist first caught attention of using gravimetry to look at hydrological signals, of course, there were a big drive to investigate the traditional hydrological signals, and much has been done in this context so far. So these examples are really only examples from a vast amount of publications done within the last, let's say, 2-3 decades. Soil moisture being one of the most important signals and processes in hydrology has been investigated, shown in this example in a study by Benjamin Kreuzfeld at the Wetzel Observatory run by the BKG, where a combination of velocimeter data, soil moisture sensors, and gravity data showed how this gravimetric signal and measurements can improve the hydrological point of view of looking and looking at this data. Groundwater is also one of the key things that were one of the first to be investigated with gravimeters by hydrologists. And as you can see in this example plot from publication from Bruno Meyers, it's clearly visible how the groundwater, the water level variations are visible within the gravimetric observations. Really nice approach done recently by Van Kamp et al. Was the idea to tackle this problematic, let's say, process of evapotranspiration. Problematic because it's a really small process. I will come to this back later. And he had a really, or his team had a really good idea in stacking a 9-year-long time series in order to resolve and get a better understanding how this small mass change within the course of 24 hours affects and can be made visible by using gravimetry as additional recording methods. Also relevant in many parts of the world is snow as, let's say, a more temporary source in hydrology to water storage changes, and there have been quite some investigations and publications also been done on this topic, showing that this is clearly resolvable by the use of gravimetry. Really important for hydrologists also is the Beddoes zone. So below the saturated, above the saturated zone and below the classical soil moisture relevant zone. And interesting about this zone is that it's really hard to take samples. So depending on its depth and extent, it's hard to make physical soil samples or to estimate and measure parameters, for example, used for hydrological modeling. So this was a really interesting approach by the group from Christensen from the University of Denmark, where they use gravimetric data to calibrate van Genuchten parameters used for hydrological modeling by the use of gravimetric data in a controlled field, infiltration experiment. So this was a really nice work showing how gravimetry is useful and can be actually used for getting a more insight about this hard to reach zone, but so relevant for hydrologists in general. Another really interesting study done by our group, by Günther et al., was showing again at the Betzel Observatory how superconducting gravimeters can be successfully deployed in a field, so in a field enclosure, and not how traditionally set up in an observatory, and what the advantages of this field setup for us as field hydrologists is. So in this plot, for example, you show you can see that there's a clear different information content visible by, on the left side, the observatory gravimeter and the field gravimeter iGraph on the right within the first top 2 meters, and how changes in water storage within these 2 meters of the first soil moisture information layers is perceived by the gravimeter itself. Most recently, our group also published something on subsurface water distribution processes, and we showed how each hydrological key process relevant for distributing water differently in the subsurface has its unique and characteristic shape of the gravity response curve. So this shows and underlines also how we can use this non-invasive method of gravimetry in the field to look at hydrological processes. But not only advances, there are still some challenges. One of those coming back to this issue of these small signals. So in this case, evapotranspiration. As I said, Van Kamp had a really nice approach of stacking time series. Prior to his publication, we tried in a data set in Western Germany to get a direct idea about how we can use gravimeter time series to extract information about this evapotranspiration process. And we found it really hard because this signal of evapotranspiration is so small that we were not sure how big are our measurement uncertainties, how big are other uncertainties, and how reliable are actually our information content we get from this gravity observations. And this led to another publication from our group about correction-induced uncertainties. And I know this is a quite big plot on the right, but if you focus on the most lower part, where it reads all on the left side of the plot, you can see that in the frequency range between, let's say, 3 and 24 hours, when you look at the uncertainties, so the root mean square error that comes from the uncertainties from correcting global hydrological, global atmospheric, non-tidal ocean and tide corrections, there's still a relevant root mean square error, more or less around 3 to 4 nanometers per second squared, which is, for example, for the process of evapotranspiration, quite important and can make it possible or not, depending on the quality of your data, to look at this process. So this is something that's still quite a challenge. Well, with respect to device precision, one has to say that obviously this increased tremendously from the instrumental point of view, but still with this slide, I want to underline how important it is to be aware of what device to use in the field of applied hydrological field research, to look at what signals of interest. So with a repeatability of more or less 5 microgal for CG6, we found in a pilot study that it was rather hard to resolve small and spatiotemporal moving precipitation fronts occurring at rather small time periods with this relative campaign method. So this is something we are working on, and that is still, I think, sometimes a challenge depending on your setup. Another important thing is that sometimes it's important to step back and have a broader idea of what local phenomena can really influence actually a time series. So this example is again from Betzel. In green, you see the total water storage based on gravimeter data, And in blue above, you see data from soil moisture sensors. And as you can see, this is a quite long time series with 19 years of data. And if you would look only at 1.5, or maybe 2 years of a subset, you might not be able to catch and have an idea what's going on a long-term storage. So either a recovery from a drought event or the direct influence from a drought event, because soil moisture looks actually quite regular and okay, and seems to recover much faster. But in the long term, the gravity stores and makes visible information that people who process and understand and interpret this have to be aware of and take into account. So much has been done in this more traditional hydrological signal things, but as we had 2 very interesting presentations about the AQG, I want to give you a really small glimpse in how we used the AQG in a field campaign last year in Betzell, measuring more or less hydrological signals also. That was our idea. So you can here see the setup. We have the AQG in its blue temperature hoodie, let's say, on a pillar. We have bordered with blue the windshield that we constructed in order to protect it from wind during the measurements, and most important for this field setup is shown in red, the mobile device we used to carry the AQG from location to location, and which hosts both the power supply and the laser system, and then during moving with the vehicle transports the AQG. So this was the setup we used. And the advances we could see in this setup was, I think, most of all, measurement time. So doing outdoor measurements with an absolute gravimeter was really a really good experience, and it worked out actually quite well. And one of the biggest things, as I said, was the advance in taking only 30 minutes for assembling and disassembling the whole setup of the measurement of the gravimeter at the pillar. So this saved us a lot of time, also because there was no cable detached during this setup. And so the AQG was actually running all the time on more or less operational temperature. The atom collection was stopped, but is not comparable to a complete cold start of the instrument. So with this setup, we saved 1.5 up to almost 3 hours sometimes in preparation, depending on outdoor temperature, and reached feasible measurement durations of, let's say, an hour or a little bit more. And this was one of the other advances we saw. Stability. So individual measurements by an AQG in the field were quite stable. There were more noisier and sites with lower noise. At the lower noise, we can say that the standard error of the mean was below 1 microgal within less than 60 minutes, sometimes even a lot quicker. So the individual measurements were really super stable, and that was good to see. But one of the problems we saw was the issue of repeatability. So as you can see here, we have 4 sites, including the one at the observatory in Betzell in Bavaria, operated by the BKG, where we had an overall repeatability of more or less 4 microgal. And this is a relevant magnitude for hydrologists when you think about precipitation events again. So this is something that is a challenge, what we have to address in the future, also by the community, I think, in general. One of the other things was the tripod. I just want to quickly mention this. We sometimes found the tripod to be quite lightweight, so you had to take care that it was not moving while you put the AQG on top of it. And in one of my questions earlier for Vincent, I mentioned this. We saw mostly due to temperature contrast, I think, trending tilts within the first 30 minutes, which was quite high in influence if you think about the possibility to measuring only 1 hour or maybe 90 minutes and then have to be cut off the first 30 minutes. That's quite an influence. So this is something we have to take care of and look more into detail. And another thing is that due to the size of the tripod of the AQG, we had to use additional improvised tables, let's say, to fit on the existing pillar structures we find in the field, not only at Betzell, but all over Germany and I guess all over Europe. So this is a thing what needs be resolved for flexible field campaigns. And one thing where I don't want to talk about results, but just to give an idea about this for you to have in mind, it's still not really easy to judge what happens to the measurements, and this definitely affects repeatability. When you measure at one location, like shown here in example A, then lay the AQG for 30 minutes horizontal and then measure again at the same location, or even as shown in B, not only laying it horizontally, but even moving around and going maybe to a next location or coming back to the same location. How will this affect measuring it? We find it really hard to judge this error or judge this possible uncertainty. So this were our impressions by taking this AQG to this wonderful field campaign supported by our colleagues from the BKG. And a really quick idea about hybrid gravimetry. So most of you are maybe familiar with this context. Hybrid gravimetry has the idea of performing relative gravimetric measurements around a base station or reference station, you can call it what you want, where there's continuous monitoring, more or less, of gravity, and with your usually relative gravimeters, you go around at different field locations and sample and measure there in loops with respect to the base station. We did that with CG6. Well, our campaign in Betzel was more or less something similar with an absolute gravimeter, so with the AQG. But yeah, the idea is to combine this to get a more spatial idea of how gravity changes are distributed in a certain catchment or an area of interest. So one of the first publications in that topic was by Jack Hindra about hybrid gravimetry, and they showed on their iGrav site in Africa that this concept can be successfully applied to get regional gravity maps, so with spatial distributions. The same is true from a publication here on a geothermal field in Iceland, also carried out by the group from Jack Hindra, where they, with a quite large measurement campaign and a lot of efforts, showed how this can be really helpful in getting an idea about the 2D distribution, about where more gravity changes or mass changes in the subsurface mostly happening. And another interesting idea and approach from Quentin Chaffot, also within the Hindra group, was the one about topographic admittance maps and how this can help to investigate different site characteristics within a hydrological catchment in France here. So what are the challenges with respect to hybrid gravimetry? Well, network preparation time, I would call it, is one of the major challenges. So obviously it's time consuming to prepare and to location scout your network. In the figure below, you can see an example about some fixed points. They're not all gravity pillars, but they might be useful and usable as gravimetric pillars for measurements of relative campaigns. And you can see there quite a lot. This figure has an extent of more or less 10 by 12 kilometers. It's around our iGrav site in northeastern Germany. And finding the right spots for your campaign are time consuming. But okay, once you invest that, then you have your network and you can carry out your hybrid gravimetric campaigns. But you're limited in flexibility when you think about event-based campaigns. So think about this moving precipitation fronts, for example. You're not really flexible and looking at new points because you have to be fixed on your network, what has been set up. So this is something that that is interesting for hydrological studies with a temporal spatial context, also especially looking at event-based measurements. Another thing, I think everyone measuring with relative gravimeters is pretty much aware of that, but for the sake of completeness, you obviously need to guarantee a reproducibility of your setup. This can be easier or harder to achieve depending on how accurate you carry out documentation. What additional measurements like height, orientation, pillar stability you carry out regularly on a regular basis in order to guarantee that you're coming actually again back to the very same spot when you do a second round or come 5 years later to the same relative gravity network. So this has to be taken into account. And quite well shown and addressed by Kennedy in a publication is the problem about the transporting drift. So when you transport gravimeters, I think we're all aware that there is the possibility of a drift, and it's hard, or sometimes it's hard to judge how big is that. Of course, you can take a lot of time and run a lot of loops, so going back to the base station, back and forth, and this can partially avoid this problem or make it easier to quantify it. You should also carry out a network adjustment, and there have been many suggestions on how this transport drift can be handled. Also, a lot of them addressed by Kennedy and his group from the USGS. But the problem is when the magnitude of this error range is in the same order as your signal of interest. So when you think about the hydrological signal you want to look at with this campaign or with this research subject. So this can be a problem. It's not always the case, but this can definitely be a problem. Nevertheless, I see a lot of high potential in this hybrid gravimetry context. And coming to the last point, not often talked about, I think, and still quite important, data processing. I mean, there's some things where we're all aware of, some things which I'm sure all the groups and processors, people who work with this data are aware of and do that. But still, I just wanted to address this because I think it needs further discussion and sensibilization within our community. So sort of state of the art, we all know corrections have to be applied depending on our signal of interest. So there are large scale effects like tides, atmosphere, global hydrology, non-tidal ocean loading. There are local corrections, for example, the local hydrology or terrain lifting and maybe even other relevant phenomena with respect to volcanoes or geothermal activities. And we have device-specific corrections. So each device is, well, as you know, different in its drift behavior, how you estimate that. Do you measure it? Do you just process that with a mathematical function? How are temperature effects? So all this is pretty well understood and carried out, and also in most studies as I find addressed. So that's good and important. But one thing is, how do you actually, or how is one processing its gravity data? There are many devices. All have individual file formats. I mean, the TSOFT format is sort of quasi-standard, but still, all manufacturers use that a little bit in a different way. Information is stored in different lines. They all have to fit into the processing chain of individual groups or persons. Maybe one operator started to program gravity processing for a group in Python, and the next one is using MATLAB or Fortran. So all these different types of information have to be combined to be more effective, also on a long scale of the time, to be effective for a research group, for research, to do fast processing of data, to get an idea about results, to get an idea about quality control of data. All this has to be condensed and individualized, because processing routines have to might be adjusted. iGraph data is processed differently than CG6 data or the AQG data, and I think this has to be thought about. Sometimes manual steps are necessary and unavoidable. Sometimes maybe it's possible to automatize some processing steps. Is data retrieved via physical connection to device or remotely? All these questions are handled differently and are handled and addressed, but I think this is something that we have to be aware of. Big advances have been made or advances with respect to standards or sort of quasi-standards when you think about the data processing context. So definitely really nice that we have data collections such as iGETS or the growing AGraph database by BKG. As I mentioned, there are sort of quasi-standards and processing routines, but these are exchanges within publications or a personal exchange during conferences or during workshops such as this one. And there's no really official standard agreed on how to process that. I mean, in the IGETS database, a lot of this additional data corrections is stored to make it reproducible. And this is good, and this is the right direction. But I just want to say that there has been made some advances, and there's still some things that can be improved, I think. With respect to software, there is sort of quasi-standard software. So Eterna is used by most groups for tight parameter estimation. Tsoft is a widely used software package also for tides and time series. mGlobe, maybe some of you know, for large scale effects, and then SGP adjust or the going pi graph for relative gravity campaign processing. So there has been made quite some effort, and this is good. And I think we just have to continue with this work. Because what are the challenges? Well, to address or to get only one idea about this correction issue, in this plot you see global hydrological effects from 6 different models for a time span of more or less 2 years. And you can see the y-axis in the scale of nanometers per second squared. These are magnitudes that might not be that relevant when you look at volcanic activity, but for hydrologists, they are quite relevant. And it depends highly on which of these global hydrological models you choose for your correction. Who chooses that? Who decides on what basis? How is this documented? This is often not explained why we chose this or this model in publications, for example. And this makes it hard to be reproducible and understandable to the most small detail. Well, more and more interesting within joint projects is maybe data sharing or even near real-time data sharing. So when you carry out joint field events campaigns and you want to share data with your partners, maybe when you think again about a quite fast evolving precipitation front, you need the idea about where did I measure now, where should I go in 2 hours or tomorrow? So how do I exchange the data? This can be done in various ways, and there's not the right way or the best way, but they all have to adapt to your own programming system, to your own processing schemes, to the processing schemes of your partners. So there's no real standard in this. It doesn't matter if you provide data via APIs, a cloud service, or send them around by email. When you share data with partners, you also want to do a quality check and sort of quality assessment, because yeah, it's somehow releasing your data and you want to guarantee that it's a good work. So you have to think about these types of issues. The same is true for maybe near real-time data visualization. I mean, every group and they can obviously choose their own solution, and there are many options out there how to do that. But I think it's good also for controlling instruments to have a regular look on automatized visualization of different parameters, not only the gravity value itself, but all the additional data that gets spit out sort of by the gravimeters and by this overall monitoring system. And maybe with respect to this data processing, one of the most interesting or important things is the reproducible workflow. So if all steps are carried out within, let's say, personal scripts manually, there's quite error prone. So a standardization of routines, especially if you have to manage many different stations and different devices, is really the basis for reproducible processing. Going back to understand how did I process this data 5 years ago or last year? What is my workflow? How do I do that for all the different stations? So thinking about this and making this shareable also within the community or within data publications, I think is something what is still a challenge. Well, we have been working on going into accepting this challenge a little bit with the Python toolbox we developed. Hydrograph is the working name, where we address these types of reproducibility for processing in terms of data storage, filtering, corrections, global effect calculations, producing residuals, so the overall final product, let's say. So far it works with GFON data, iGraph data, but CG6 and AQG data is about to be released also. And yeah, it's open source. Everyone is invited to use it, to contribute. I think it's highly customizable, and maybe if you can have a look and are interested, then I invite you to join in and think about how do I make my data processing reproducible and this way more easy to explain and share with other people of our community. And with this, I want to sum up in saying that, well, much has been done with respect to more common or traditional hydrological processes. A lot of advances have been made instrumental-wise from the device precision, methodologically. There's also been a lot of advances, and just some of the challenges I listed here, I think will be addressed by the community, by some people in the future. And it's just important that we keep up thinking about these things and yeah, to go further forward and into this broad good future with gravity data, not only for hydrology, but also for geothermal or other natural phenomena investigations and expanding this method of gravimetry even further. Okay, thanks.
Thank you very much, Marvin, for the very informative talk. We have one question by Roland. I encourage you to be quick because we are a bit late. Yes.
Okay, thanks a lot, Nora. Yeah, I will be quick, Marvin. Thanks a lot for this presentation. I found it full of very, very important information for those who do gravity measurements in the field. My question is related to the aspect of repeatability you addressed in your talk. I remember that you said so far it's for us, so for you, quite difficult to make a specific statement about the repeatability. And I asked myself, where does it come from? Is it just a time question? Because you would have to set up a couple of experiments to figure that out. For instance, does it depend on the duration of a transport or whatsoever? But from a process point of view, it's pretty straightforward to investigate repeatability.
Yes, that's right. From a processing point of view, it's straightforward. The thing is that we found sometimes the problem that we come back to a site and we have a let's say a problem in this repeatability issue, and sometimes we come back to the site and it's all straightforward and works out all fine, and it's within the 1 microgal. So this is why we so far did not understand completely, but you are right. This is addressed, and we are in the process of doing and carrying out these tests in order to get a better understanding, because from the processing there's no problem obviously, but we need more data to dive into this topic and to get a better idea about the root causes or the possible root causes of this issue, and why it sometimes occurs and sometimes it does not. From the data we have so far and from the processing we did, we cannot, I do not want to say something about this because we don't know yet what are the causes. But I think as soon as we get more data and do more of these campaigns, then we will definitely get a better idea about this. What's the root? Yeah.
Got it.